In this video, Rina Ibragimova told us how she got involved with machine learning and then picked out the highlight from her lecture.
My name is Rina Ibragimova. I'm a postdoctoral researcher at Aalto University, and I'm also a co-organizer of this wonderful training school we're having right now. So let's start with maybe my journey, how I even arrived to where I'm at now. Well, it all started with some sort of coincidence, and at some point it was even a small worry for me, because I was studying in a technical university, but it was all dedicated to nuclear reactors and the material science for nuclear reactors. And in my latest years of my university studies, I couldn't get a clearance form to continue with this work. So I had to choose theoretical modeling instead of experimental work. And back then it was a big worry for me, because I thought that all my studies just went for nothing and I cannot continue with that. But that was transformational for me, because I started atomistic modeling. I started to learn quantum chemistry, quantum mechanics, and studying materials, electronic structure of them, changing the applications, whatever I was fascinated with. It was solar cells at some point, and some other semiconductors, two-dimensional materials, many different applications. That's how I came across this, at that time, very emerging field of machine learning interatomic potentials, and I was really fascinated what you can do with it if you train a really good model. Then several years of learning how to actually train those models and look at errors I was getting from adding this data and other data and so on, and arrived to the point where my model actually worked, and I could do some bigger systems, and not only that, but unify the description of molecules, some hydrocarbon molecules, simpler and more complex molecules, in the solid state, some crystals and amorphous hydrogenated carbon. And it's all under the same hood of this machine learning.
In her lectures, she showed how machine learning models can go beyond physics-based ones and data-driven learning ones to accurately describe atomic interactions. As an example, she modeled a system of carbon and hydrogen, firstly in a crystalline structure under extremely high pressure and temperature. And then calculated for lower pressures, and then repeated for higher and higher temperatures. She demonstrated that the machine learning method was able to calculate the structures of the crystal, the liquid, and the gas phases.
And it's all under the same hood of this machine learning interatomic potential. That's great. Where can we use this potential, I thought, and then I came across some astronomers and astrophysicists who were actually interested in using the machine learning interatomic potentials for astrochemistry applications, and that's how it all started. It's still an ongoing process, and hopefully I will do a little bit more in the future with that. So yeah.